Hey everybody, welcome back. This is a follow-up video to the work that I've done on implementing compute shaders in Godot to simulate 100,000 Boids. I want to spend some time to talk through some of the techniques I use to debug the shader, particularly with spatial binning as well. So today we're going to implement a few different things. The first is the ability to scale the Boids. We never hooked that up, so I'll show you how to hook that up. And then for the binning, a couple things that I found useful. One, the ability to show a grid where you could actually see where the bins are. In addition to that, I've implemented a view mode that will color the Boids based on the bins. So just an alternating checkerboard that the shader will write in here so that you can see the Boids are actually getting into the bins that you expect. So you can see they do line up with the grid lines here. And then finally, detection view that will pick a particular Boid and highlight the bins that it's looking at, as well as coloring both the friends and the avoids that it finds. And so the last thing that will also show is how to print out information that comes back from the compute shader. So all very useful things if you're going to be working with compute shaders and particle shaders. So I hope you enjoy. One of the things that will be helpful for us as we increase the number of voids is the ability to control the scale. So we already put a uniform scale in our shader, but we haven't connected it to our GD script yet. So let's do that. We'll do export range. We'll go from 0.1 to 1.0. Let void scale. Set it equal to 0.5. We'll use our setter and getter here. New scale. And then void scale equal to new scale. And we're going to need to do this again. We need to set this in our shader. So we need to check if it's in the tree. And then we'll set the scale uniform. You can see down here, scale, scale. And then this will be void scale. And the last thing we need to do, I missed a. Okay, the last thing we need to do is set void scale equal to void scale. Now, if we run it, we should be able to change the size of these guys. Make them bigger, make them smaller. All right. An easy way to check the data from the compute shaders is to do something like this. Get the buffer data back after you've run the shader and then run the sync. In this case, we're going to pull the bin prefix sum buffer out. You need to convert that to 32 in 32 array, and then you can just print that out, bin prefix sum. And what we know is this should, the last number in this should be the cumulative count of the Boids. Now I don't want to do this for 20,000 Boids, but let's just do 100. We'll run it, take a look at the output, and see if it's ending up with at 100. So here you can see the cumulative count that's coming back after it runs the calculations, and you can just sort of scan the numbers and see that they seem to be increasing, and at some point they do end up at 100, which is the number of voids that we have. Now I'd like a way to visualize the grid, and to do that I'm going to create a new folder here and create a scene that is capable of drawing this grid. So scene, 2D scene, I'll call this grid. to add a script. And this script is going to be pretty simple. We're just going to clear this out because we're going to end up using the draw function. So we're going to take a couple of variables, the bin size, the number of bins in the X, and the number of bins in the Y direction. We're going to implement the draw function. So when you're drawing within a tree here, this is how I usually start this. Basically inverse the global transform of whatever tree I'm in. And then I'm going to draw the columns with this, and then going to draw the rows for the bins in the Y direction. So this is draw function that gets called every frame. I'm going to draw a line, one for each column and one for each row. Okay, so I'll save that. And then go back to my main scene, and I'm going to add this grid to the main scene, and then I'm going to set those variables in the onReady function here. So I don't know, let's do that here after we calculate the bins. All right, so let's see if this renders the grid for our Boids. Okay, there you go. One of the things I've found that is useful to be able to do is to pause the simulation. And so we're going to add a variable that allows us to pause. There's several ways to implement this. I just want to pause the compute shader for this example. So I will be hooking up a variable that we pass in the compute shader and then basically stop updating the position and velocity of the Boids. So export variable pause, and we're going to start with it unpaused, and then we'll use our set new value, and then I need to pass this in. Okay, so let's see what happened here. So we've got our pause variable over here. Actually, I want to make a new section for this. Let's call this, let's just call it other for now. So down in our other, we've got our pause function, and I need to pass this in to the compute shader. So I'm just going to add this to the parameters that we pass in with our parameter over here. So after the delta, after the time, I'm going to add that pause variable. Now we'll need to go to the compute shader to connect that. Now in the compute shader, in the shared data, we need to make sure that we add this. It's not really a float. It's more of a Boolean, but we can pass it in as a float since we have this buffer. Basically, it'll be 0 if it's false, and anything that's not 0 will register as true. So we just have to know that. And then in our simulation, we're going to check that variable down where we update our position and velocity. So let's go here and check if it's converted. I'm going to convert it to a bool, and if it's not false, then I'm going to update my position and velocity. If it is false, then I will not do that. I need to make sure that you save this. Actually, we need to save both these. We'll do file, save all, both. both the shared data and the simulation. Now, if I go back to my scene here, let's disable that print statement just for this test and see if we can get these things to pause. So here's main, pause, it's unpaused. Okay, the voids are flying around. Sorry, I'm going to turn this to solid so you can see them a little bit better. And then if I hit pause, you can see they're all frozen. And then if I unpause them, sorry about that. All right, then they're unpaused. So that is working. The other thing I'd like to do for completeness is put a setting in that would allow us to turn on and off the grid. So let's do export grid. Let's call it bin grid. Bin grid. And we'll start with it off by default. And then set new grid bin grid equals new grid. And then if is side 3, then on my grid visible equals bin grid. Now, again, we'll have the same problem here, so we need to set bin grid equal to bin grid. Now we have a flag to turn on and off our bin grid. Let's pop this out. Let's run this. Bring this down. Okay, the bin is off. Bin is on. We can pause. We can start. So we're starting to get some control that would allow us to compare data to what we're seeing here. That's why we're setting all this up. Okay, now we have the ability to pause our simulation. We can look at another buffer. So the bin sum buffer will tell us how many Boids are in each bin. So if we run this, set this up, and this way we're putting on our Boids here. We can pause the simulation and we can look at this as it's printing out. We can see we've got 0, 0, 0, 1, 1. 0, 0, 0, 1 Boid, 1 Boid. Actually, what I found as I was playing with this is this pause function up here works just as well to be able to pause the results and look at the output 0, 1, 0, 0, 1, 0. So again, another way to visualize both what you're seeing on screen and the data that's coming back from the compute shader. Before moving on to the next shader debugger, I'm going to disable this output because we're going to be turning back up the number of Boids, and I don't want that to be slowing me down. Before we wrap up, there's two other visualizations that I would like to share with you that were helpful in particularly the binning. The first is, we've drawn these green lines where we believe the bins are, but how do we know for sure that the shader is actually putting the Boids in the proper bin? We looked at the sum data arrays, so we have some idea that things are working properly. Obviously, we've got performance increase on this. And then the other question is, how do we know that a Boid, a particular Boid, if I pause this for a second, how do I know that this Boid is only looking at these bins around it? And is the friend radius falling within those bins? What if the friend radius was bigger and I'm missing out on some of the friends that I should have for the flocking simulation? So we'll implement two additional visualizations, color visualizations to help with that. In order to implement these new visualizations, I would like to pass in a color mode to the compute shader as well, because there's some additional data or some additional steps that we'll need to take in the compute shader in order to implement these. So in addition to pause, I am going to pass in the void color mode to the compute shader. And then I come over to my compute shader. I will add that here. Color mode, and I'll be using this in the simulation shader to do different things depending on what color mode I'm in. So we're going to add a color mode that colors every other bin a different color. So what we should get is a checkerboard pattern of all the bins, and that color will be set from the compute shader. And so in order to do that, with the color mode, we're going to go down to the bottom of our function. We're going to make a switch statement, much like we did in the particle shader for these different color nodes. I'll show you why in a second. So far we have three color modes. We have solid, we have heading, and we have friends. And only one of them needed to use this alpha variable to store the number of friends. This is right here. I'm going to convert the color mode from a float to an int because a switch statement needs an int. And so this should work properly to convert that float. Again, maybe you want to make a separate buffer of ints for this. I'm throwing these into the float buffer because it's convenient, but it does cause some of these casts to become necessary. Okay, so let's make a case 3. This will be our bin shading, case 3, and we're going to do a calculation here that will color every other bin. So it's basically when you do modulo 2, you'll get even or odd, which works great for one particular row, but depending on if the number of bins you have in the x direction is even or odd, you'll get different behavior. That is, if they're even, this works great. If they're odd, what will happen is you'll end up with the same even odd across every row, and you'll get columns that are all the same color. So we have to do a check here to see if the number of bins in the x direction are odd, then we'll use this instead to calculate the 0 or the 1. And then we're going to write that value into the image store so that we can then get that back to the particle shader and take action on that to control the color of the void. Okay. Now back in the main, we want to add a new color mode for this. So let's find our colors, and after friends, let's add one called bin. So we should see that show up over here. And now we're going to add that to our particle shader. Now we're going to go into our particle shader, and down in our color mode, we're going to add a third case for this bin shading. And we're going to check the alpha value, which stores a 0 or a 1. We're going to convert this to a bool, since we know it's going to be a 0 or a 1. And we're going to alternate the colors between either the solid color that's set or we will do sort of the inverse of that. So color R we'll do 1 minus that for each. Do a back for and now we gotta make this float. Green, blue, the alpha will just be 1. Actually, the alpha, we will maintain whatever the alpha is for color. Okay. And then let's put our break. And that should do it. With all of that connected now, we should be able to run our new color mode. So let's run our simulation. And we'll set this up again. Now if I switch to bin mode, so bin color mode, bin, what you see is, and hopefully you can see this. I know there are colorblind concerns. I think, here we go, blue and orange are supposed to be highly visible, I think, for everyone. So hopefully you can see this. But basically what we notice here is the color of the Boids is lining up very nicely with the lines we drew that represent where our bins are. So this is great news. It means that for each bin, it is writing in a different 0 or 1, and so we can visualize that yes, these are in fact being set properly by the compute shader. This is has been one very helpful debug method. So with this last color mode, what we want to do is set up several different types of Boids and give them each a distinct color. So a regular Boid will be this blue color. Any Boid that we're looking at in our bin, so yellow is our Boid of interest, we will color white. Any Boid that's in the bin circle we want to, or in the friend circle, we want to color green. If you're in the avoid circle, we want to color those Boids red, and then yellow will be the Boid that we're tracking. The way we're going to do this is similar to what we've done with the heading and the friends. We're going to use a texture map. I just make a note that if you're looking for cool palettes of colors, this low spec website has some awesome pixel art type palettes. So I went and found a high contrast palette, an original Lego palette. I'm going to use this, but instead of using the UVs, we're going to actually pick the specific pixel that we want in this case. So that is a texel fetch call where you give it the texture and then the texel position, and I believe this is the bitmap level. And so what we'll do is for each one of these Boids, we'll give it a different number between 0 and 4 to correspond to the different types of Boids. We'll do that in the compute shader where we do our checking, and then in the particle shader we will map those using texel fetch to 0, 1, 2, 3, 4 to get the different colors. Let's implement the detection mode in the compute shader. So one thing that we need to do first is remove this because you see now we're doing this down here in the switch statement. I should have done that when I implemented that. So clean that up. And then with this color mode, we're going to need this higher up in the function. So I'm actually going to make a variable and use that instead. I want to get down to the switch statement. Okay, and then we're going to have our case 4, which is where we will handle this detection mode. We'll come down and fill this out later. Now, if we go up here to the use bin, if use bin, when we go through and find the Boids in the bin, figure out if they're friends and the Voids, this is where we want to put in our detection type. So we're going to make a variable called detection type that we'll use. And we're going to initialize it to 1, because if you've gotten in here, that means you are in one of the bins that the Boid is checking. So we want to give you a unique color from just the regular Boid, which would be 0. Then if you get into the friend group, you will become detection type 2. If you get into the avoid radius, you will become detection type 3. Now we haven't set that on anything yet. So once we have that detection type, and we want to do this still within this if statement, then we're going to check two things. One, we want to see if this is the thread for the Boid that we're keying off of, and we're using index 0. It doesn't really matter what index you pick, you're just basically trying to get this visualization for any Boid. So we're using 0. So if this is the 0 Boid, then we're going to color things by the detection types around it. Params color mode 4, actually we can just use color mode here because we've stored that as a variable. And then what we need to do, this is important, is if you remember, these are all running in parallel, so you don't know which Boids have already written their positions to the texture and which ones have not. So in order to protect against that, we need to get that texture, pull the position rotation information out of that texture to ensure we don't overwrite it, and then we will write the detection type into that. So these first two things, this figures out what pixel position from the image using the other Boid index, the other index. Then we read out the position rotation, and then we will write back in to the Boid data texture using this pixel position, the position rotation that we just read, plus the detection type. Close that off. Okay, and then down at the bottom, in this case statement, we actually need to do a similar check. Again, all of these Boids are running in parallel, so there's a chance that some of these have already written their detection type. So when you go into them and you want to write out your position velocity or your position and rotation, you don't want to overwrite the detection type. So we need to get that and store it. We'll store that in the detection type down here. And then there's a special case where if we are Boid 0, which is the one we're keying off of, then we want to set our detection type to 4, so we'll be highlighted as the Boid that we're tracking. And then finally, we'll write that information into the image. Last thing we need to do is over in the bin sum, we want to make sure that we clear the detection types every frame so that the old detection types don't stay in there. And in order to do that, we're going to check when we spin through all these Boids, we clear out the sum, and then we add up the sums for all of the Boids. We're also going to check to see if we're in color mode 4, and then get the position of yourself so you can write in the image store all 0. So this will clear out position, rotation, and the detection type. So save all of these. Let's see if we can get this detection map set up now. So in my particle shader, I'm going to add this detection map. Let's see. Let's see that. 1 second. Okay, so there's a detection map. that we're going to use to color code these. Let's go into our shader, and we want to be, this is important, we want to be in this void particle shader. We will make a new, let's see, uniform sampler, duty, detection, just like we did before. Should see that pop up. Okay, there it is. Drag and drop our detection map in there. It's kind of nice, you can see that easier. Let's go down, let's add case 4. So case 4 is going to be this detection case. Jeez. Our break. Now let's set the color equal to pixel fetch. We want our detection map. IVEC 2. And we need to convert our void pos rotation alpha to an int. That will give us the detection type in the x direction. Then it's always 0 and y, and we have 0 LODs. So that should set our color from the detection map, 0 being this blue, and 1, 2, 3, 4 being the yellow. Now let's go up to our menu for the color modes, and let's add detection color mode. Should see, come here, bin detection. All right. Now let's come back into Godot and run this and see if we get the visualization that we're hoping for. So we're on detection. I'm going to make this floating. Run this. Okay. Let's see what we're looking at here. I'm going to, when this comes up, I'm going to pause this for a second. What we should be seeing here is the yellow is the void, so that's void 0. Any reds are voids, any greens are friends, any whites mean that those are voids that we checked. In the blue are all of the other voids. So what we want to show here is that, yes, yellow is actually only checking in these surrounding bins. And so you can actually visualize what's happening and ensure that the code is working properly, because these colors are all coming from the compute shader as it goes through and detects the bins, the friends, the avoids. The other thing you'll notice is that the friends are easily within these bins. And if I turn up the friend radius all the way to 50, you'll see that they're still handled pretty well within this. What I found is 50 is way too big to get good simulation. So actually, a number 20 or below, and then same with the detection or the avoid radius, you can turn this up and down and see the voids change color. Usually I set the void radius to be about half of the friend radius. So there's a chance, given the size of this, we could go even smaller with the bins and get more performance. So right now you see we've got 20,000 voids at 230 frames per second. Let's see what happens if we set the number of voids or the bin size. Let's make it smaller. Come on here and find this. Let's try 32. Now we've jumped to 325. And I can turn these grids off. And of course, we still have our other modes working. There's our bins. There's our friends. You can see some hotspots there. Our heading. And if we just want to have salad color, so everything's still working. All right, well, I hope this video was helpful. We learned how to print out information as it came back from the compute shader. We added some more visualization modes here to visualize which bins the Boids were in, as well as which bins the Boids were detecting. And I think these techniques can be helpful on any compute shader work that you're doing. So I hope that you find them useful, and thank you so much for watching.